Welcome to my new calculus channel. My name is John Gabriel, and in today's video I'm going to talk with you a little more about that historic discovery I discussed in a previous video, and explain to you why it works and show you how it works, and then leave you with something else to think about, which is equally historic. So let's begin. Now, you'll remember that I showed you this geometric identity on the right-hand side where my mouse is hovering. And from this here, all this knowledge is realized. And I've explained this geometric identity in two articles. In one called Fixing Your Broken Mainstream Calculus, in which I show you how to fix both your derivative and your integral. So I give you two definitions, new definitions, this definition and also the old one for derivative. And then I reveal this historic formula to you of how you can find the derivative with the slope, the numeric slope, at any point using any function with exactly the same formula, this particular formula here, and all you need is x and the function, nothing else. Okay, so I'll place links to these, and you can then look at those, and I'll also put a link to this applet so you can see what's going on by playing with it by yourself. Okay, but in any case, so what I wanted to show you is that all you need is the x value of this point and the function name. So you don't even need h, because it will work for any h. Okay, so as I've shown you before, it doesn't matter what h you put in there, it will still give you the correct derivative, because the slope of the tangent line doesn't depend on h. Okay, only the slope of the non-parallel secant line, which is this red line. So let's just make it big again so we can see what's going on. So, okay, so I've made it nice and big now, and you'll see that this identity here, which is this first line here, this the ratio slope of the non-parallel secant line is equal to the derivative plus this expression in Q of h, which in fact turns out to be this value that you see on the right here. And all you need here really again is just x and the name of the function. f2 is the length of this line here. Okay, so this line here is f2. And once you find that, you know h, so you know the slope at that particular point. Okay, so it's pretty simple. And you can see the derivation of that in one of the articles that I'll put in the link. And to see it work, we can go to, here's a quick derivation of it, but in any case, you can go to this button here, and it doesn't matter how you move this along, you'll see that it'll always give you the derivative. Okay, so now, if we change that, let's say, to something like absolute value of x squared. Now, strictly speaking, straight lines don't have derivatives. They have slopes, but not derivatives. I mean, it's only called a derivative if it's tangent to the nonlinear curve, okay? And so, in fact, this here just gives you the absolute value of x squared, and if you take the square root, should give you this function here. This is the one I was talking about. So over here, you'll see it doesn't matter what is h, okay? It'll always be the same value. And of course, there is no derivative down here at the value of 0. I'm trying to get it onto 0 there, simply because there are many possible tangent lines there, okay? And so there isn't a derivative. And in fact, you can't really call this a derivative either. It's just the primary characteristic attribute of any straight line. That is, they all have slopes, okay? So this function that you're normally shown, which is really the absolute value function, is just a bunch of rubbish meant to be a time waster in your curriculum, because calculus only works when a given curve is smooth. Okay, so the methods of calculus do not apply when a given interval of a curve is not smooth. But what does it mean to be smooth? Well, first of all, it means that it must be continuous. In other words, that there cannot be any undefined x's in that interval. And secondly, it means that you can only produce one tangent line. That's also important because the mainstream definition of tangent line is wrong. Okay, it became wrong after the idiot Cauchy and Weierstrass tried to rigorize calculus. They failed miserably, as this proves to you. One of the things that Cauchy said is that he had to remove algebra to define the derivative. Well, what you're looking at in front of you is proof that you can do it using geometry. And if you can do it using geometry, you can do it using algebra. So this not only exposes mainstream ignorance on a grand scale, but it shows you how you can find the derivative geometrically. Right, so I hope I've explained this a little bit better, and I wanted to tell you also that you can use this particular identity to discover a special theorem about the area under a particular curve. Okay, so for example, let's just get rid of that again, here and here, and do that. And actually what I wanted to do was make it a little wider so I can pull this button down. Okay, now I could probably, if I wanted to, go back here and just do this, and that's no problem. Okay, so in any case, it's just a matter of spacing on the screen. That's the only reason why I put quarter as a coefficient of x squared. Now, in any case, if you wanted to find the area between 2 points under the curve, you can use this geometric identity. Okay, and one clue to you is that this trapezium going all the way down to the x-axis will give you the approximate value of the area under the curve. But you can get the exact value, and that's a special theorem which I'm not going to reveal. So I'm going to let you think about that, and maybe at some time in the future I'll reveal it, depending on, you know, how I feel and whether I think that I should give the mainstream morons who are constantly persecuting me and calling me a crank any more ammunition. So I want to focus right now on the basics. And if once you understand the basics and understand that your mainstream calculus is a bunch of crap, in other words, the formulation is a bunch of crap, then I'll reveal a little bit more. And now I'm terribly out of breath. I'm going to upload this video to BitChute, and if you're not already a subscriber on BitChute, you're obviously going to miss it. So subscribe to my channel, also subscribe to my YouTube channel, but most importantly the BitChute channel, and I will at some future time try to share some more historic knowledge with you that has never been realized or discovered by anyone before me. I am John Gabriel, and this is the New Calculus channel. Till next time, goodbye.